Thank you for the quiet introduction. I won't be talking about dog sport, but before we start, I want to see a show of hands who has already looked into software security. So, I think about half of the audience who has looked into hardware security. Quite less. I think it's the reason why I'm here. So, the current state of hardware security is that most people will start focusing on the software side of things, but there's a lot to discover on the hardware side as well. So today I will give you a brief introduction into hardware security, and I hope to tinker your interest into it. It's quite easy to get started. We will talk about a couple of things. It's still a broad subject, so you will discover a small part of it. There's a lot more to discover. Make sure to come after the talk towards me. I can tell you a lot more about it. So today we will be giving you a brief introduction into hardware hacking itself without any Python. Then we will take a closer look at manipulating USB using Python, and afterwards manipulating radio signals using Python. Although I already got quite a good introduction, I'm a site reliability engineer and security specialist at Warpnet, an IT security company here in Groningen. Hardware hacking is something I do at home, so by day I do more the software side, and by night I do the hardware side. I've been using Python for infrastructure as code and for applying or doing things in the open source world. I wouldn't call myself a Python programmer. I do quite a bit of scripting, but I like to use it because I see, especially on the platform side, quite a lot of colleagues know it as well. So it's the main language I use whenever I have a task to do. So let's get started with hardware hacking. Whenever you have some device in your hand, the first thing you should do is do some research. The thing you can do is just look it up on Google to get more information about the hardware piece. It can be a laptop, it can be a doorbell, whatever it may be. If it's hardware, you can find some information on it. And sometimes you don't even have to look on the internet. There's quite a lot of information on the package itself. So make sure you read the manual. There's quite a lot of information in the manual itself. Tear it down, open it up. There might be some stickers. You might void some warranty, but if you tear it down, you will see patterns reoccurring in all of those devices. Whenever it uses radio, make sure to check out the FCC ID as well. If it's sold on the US market, then it's been tested by the FCC, and they have quite a lot of information about devices as well. If it uses radio, networking of USB or any other type of communication, you can always sniff the communication line to reverse engineer things that are going on. And for both of them, today we will take a close look of them. And if you have opened the device, there will be quite a lot of components. For all of those individual components, you can also look towards the data sheets and find some prior research as well, which always helps you get a bit better understanding of the device itself. But if you want to get started, it's hardware. You need something more than only a computer. So the basic toolkit I would advise you to get is a multimeter, soldering iron, screwdriver set, jumper wires, and spare hardware, because you will break shit. The methods to get started. The three most simple methods. What you can do with hardware is just start with a part or component replacement. Just tinker with it, replace things, take things out, see what it's doing. Another method is analyzing the inter-component communication. It's just all components talking to one each other. So watch what is going over the line, try to sniff it. And the third method, find any closed and inaccessible debug ports which are left open by accident. Today we will focus on the last two methods. So let's do our first example. Let's attack, or let's reverse a simple wireless router you have all at home. If you're not alone at home or if you have to do work this weekend, I might advise you to get a second one. So in this case, I just bought a cheap Sitecom wireless router. and I opened it, and then you see like all of those components. But there are quite a lot of black boxes on it, the ICs on the board. So they might be very interesting. But we're doing a beginner talk, so let's not look at them today. If you look closely, you see there are 4 pins without any components soldered to it. They are nicely labeled, so that might be something interesting. Like when they are developing these kind of hardware devices, you need some type or some kind of debugging port, and what they will usually do is to close them off. But sometimes the hardware developer might forget to close it off before it's going to market. So let's test and see if there's actually some communication going on this potentially debug port. So I'm using the first tool in the toolkit, a basic multimeter, and I can already see that there's some communication going over it. There is some voltage on the lines. I'm able to find the ground and the voltage pin, and I'm seeing that it is using around 3 volts for doing any communication. There are 4 pins, and because I like to spend my money I earn during my daytime, I bought an oscilloscope. So it was quite a bit easier for me to see what data was going on. But you could do the same with just a multimeter, see that there's actually some data going on, because the voltage won't be stable. You will see it going up and down. But the fact that you can already see high and low signals might suggest that it is actually there is some type of communication going on. So I suspected that it would be serial communication. If you do hardware hacking, you will see that you are using the same patterns over and over again. And almost all devices use some kind of serial communication for their debug ports. So using the oscilloscope and a multimeter, I was able to detect the ground and voltage pin. So there's 2 left. And in this case, it will almost always be the receive and transmit pin. And it's quite easy to find the transmit pin, because if you power on the device, it will start shouting things, so the voltage will be high. So, like you can see in the diagram below, whenever you do serial communication, you want to connect the transmit pin to the read pin of your computer, and the receive pin of the hardware device towards the transmit pin of your computer or your serial reader. In this case, the router itself is using 3 volts, and my serial adapter is using 5 volts. So I use an extra component called the logic level converter to make sure that I don't break my laptop or the serial converter or the router itself, because one is starting on 3 volts, the other on 5 volts. So we have to convert the whole signal towards from 3 to 5 volts and from 5 volts to 3 volts. Those components you can find quite cheaply on the internet. Just look around. If you type into Google, I want to convert 3 volts to 5, there are quite a lot of information you can find. But if you got the connection, you found the baud rate itself, so the bits per second going over the line, you can just start a serial console on your computer, and you will see something like this. If you look closely, you see that the router itself is actually using Linux, and on the end you will actually see a console. So without having to input any password, we are now in a console of a wireless router. And like the first time, it took me a day to figure all those things out, but it only took me a day to get console access to a hardware device. And like in the preparation for this talk, I was like, how to do this with Python? Let's buy another device, like a wireless camera. I tried it, but unfortunately, this one is nicely closed off. And you see in the router, the pins were quite easily accessible. They were quite big. This compact camera, the pins are quite smaller. I had to solder some small wires to it in order to get the communication going, but there wasn't any communication on the line. So you won't always succeed. Sometimes you fail, but those are the compliments to the product designer. They actually closed it off this time. So let's look at Python. We already see that it's quite easy to get some communication in regular ways with devices. Now let's see. One of the most often used types of communication towards the computer might be USB. So let's tinker with that part. We will use another tool for it because we have to use Python somehow. So I found this Great Fat One by Great Scott Gadgets. It's actually an open hardware design. So you can buy the product, but you can also just look at the design and build it yourself. It's around €100. The nice thing is it gives your computer quite a lot of GPIO pins to tinker with, because nowadays, especially MacBooks, get lesser and lesser ports for you to use. But the nice thing about it that you can talk to those I/O pins using a Python API. So the thing is, where it's somewhat the same as an Arduino, you have all those GPIO pins you can use. You can now use your computer as the brain of it. So you have quite a lot more CPU memory to use with it, and you can actually use Python. And I find it quite a lot easier than doing things in Arduino IDEs. So if we look at the Great Fat One, there's quite a big spec list. Some interesting things to note is that it has dual USB ports. We'll come back to that later. You can buy expansion shields called neighbors, and you can put them on the Great Fat One itself. And I have a couple of them extra, so if you want to buy one, come to me after the talk. I will give you one for free. And there are a couple of programmable LEDs and buttons as we are used to when using an Arduino, for example. And now, if you want to go to the Python part, it's quite simple. Once you have connected the Great Fat to your computer, you install the Great Fat library, and you can just import from Great Fat and get the device started. But now we have this Python interface we want to use. So let's say we want to let one of the LEDs blink. It's just like this. So with a couple lines of Python, we can already do something on the physical world quite easily. And the code I will be showing today won't be the nicest, but the thing is, I want to do things with hardware, and Python is just one of my tools. So we now have this great device we can use to interact with the outside world. We want to look at USB, and I want to use the Great Fat for it. So let's take a look at our second attack, manipulating USB by building a rubber ducky using Python. Who is already familiar with a rubber ducky? A couple of hands, not all. So the rubber ducky is a somewhat kind of USB-looking device, and you can write your own script for it. Whenever some victim plugs in this USB flash drive, it will execute a program. So it emulates a keyboard, and it then starts typing things on the victim's computer. If you throw them around, people will put them in their laptops. Your script will be run eventually. So I wanted to build this thing in Python using the Great Fat. So we have the host computer, we have the Great Fat One connected to it, and then we connect the Great Fat towards our victim computer to simulate somewhat a rubber ducky device. And because you would be able to do this using the standard Great Fat library, but then you will have to write all the USB parts yourself. There's actually another library called Phase Dancer you can use to make it a lot easier for yourself. If we look at the code, it's just a couple lines of imports. We will define a USB keyboard device, and then within a couple lines of code, you will see that for this case, I will press some modifier keys and T to open a terminal on Linux, and then I will type the command "who am I" to show that the user itself. So within 10 lines of Python, we already have a rubber ducky going. That's nice. You now have to hold your laptop, the Great Fat One, and find the victim who thinks it's actually a flash drive. But at least we've shown that we can use Python to do some kind of proof of concepts with the USB part. And the nice thing is, the Great Fat One can actually emulate a keyboard in this case. So the victim computer actually thinks the great fat one is a USB keyboard instead of the great fat. So let's look at our third attack, the man in the middle of USB using Python. So we will use the great fat one again. And I tried looking at home which USB device I could find. And the first thing I saw was my keyboard. So what we are going to do is that we will connect the keyboard to my own computer, then connect the great fat to my computer, and from the great fat we will connect to a victim computer. So we can actually man in the middle using our own computer and our own great fat device to get the signals from USB, be able to read them or tinker with them, and then send them towards the victim who actually thinks this is the same keyboard I'm showing here. So from a USB perspective, it just shouts that it's the same product, the same vendor, and the computer happily accepts it. So using the same phase dancer library, we can just state the vendor and the product ID, and using the great fat one, it's actually quite easy to get this information. You can use other programs on your Linux or Mac or Windows device as well. They are just nicely labeled. You can just copy and paste them in your script. And if we then look at our main entry of the script, we will define the USB proxy using the vendor and the product of the keyboard. And then we will add a filter to show what is going on the USB traffic. So if you run this program, we can actually see the bits and bytes going over the line and just one by one check out and see what they're doing. And the first thing you will know, the moment you plug in a USB device, there's coming a lot of traffic over it. But in this case, we want to keep it simple. So let's imagine we're using our Linux environment. We want to use VI, but we are still a noob. We previously used Nano, and we still want to use our arrow keys. So instead of remapping keys in our VI config, let's just hack the USB traffic to turn the arrow keys into movement keys. So that's quite easy. You can just hook in on the class itself. You can write a filter in or filter out function. So each time a button is pressed, you get the data itself, so the bits or bytes going in, and you can just remap them. So in this case, if the arrow left is pressed, we get a specific digit or specific byte or a set of bits, and we can just rewrite them to the other ones. So it's quite easy with a couple of lines of Python to actually man in the middle USB, change things around, and start doing things with USB itself. And this is just a keyboard, but imagine that you have this crypto device storing your bitcoins, and it's also needs to do some crypto with the host computer. You can start reading what's going on, and we found that there were quite a lot of vulnerabilities found by other researchers by just watching communication from the device towards the computer. So for this talk, I also tried, let's do something more fancy than just a keyboard. So I bought a nice Nintendo Switch controller, but it was getting harder and harder because normally the keyboard is quite simple in communication. For the Nintendo Switch, the code was getting longer and longer because you have to write, you have to explain to the Nintendo Switch that it's doing some setup with the Nintendo Switch itself. It's using multiple USB signals, and it gets quite complex. So I'm still working on that one. But yeah, I have another controller at home. I'm not going to use only for hacking in this case. But it gives you an insight into USB and how easy it would be to start tinkering with it. So let's look at radio. For this, we can't use the great fat one, but the other thing Great Scott created was the yardstick one. It's a radio dongle you can use. It's not used for software-defined radio, but you can use it to transmit and receive wireless signals on frequencies below 1 gigahertz. So you can do any Wi-Fi with it, but you can do a lot else. And it's exposing those radio capabilities to your computing using a Python API. So as we've been familiar with the Great Fat One, it would be quite easy to do things with radio. So some specifications. It's half duplex, so you can't send and transmit or transmit and receive on the same time, but you can buy 2 yardstick ones and do it in full duplex. So I have 2 at home. It only works on certain frequencies, but as you will discover on most hardware devices doing radio, they will use these specific frequencies because you're not allowed to use the whole spectrum. The Great Fat One is limited, or the yardstick is limited to a certain type of modulations, but I won't dive into details today on that part. And it has quite a high data rate, so high enough to do most easy at home consumer stuff. Like we're used to, it's quite easy to get it started. So we can just import the RFCAT library. We set the frequency, we set the modulation type, we set the baud rate, we state that we want to receive or transmit on max power, and we just start listening. And then on your terminal, you will see raw data coming in from the outside world. And while I was doing that, I saw that, for example, my neighbor's thermostat was using the same frequency as well. So it was just shouting every couple of seconds with their home temperature. So let's do a simple replay attack, or at least I find them simple by now. So I went to the store again, and I bought a simple switch controller. So to turn off your lights. And if you look closely to the packaging, it already states the frequency itself. And in this case, we will be using the yardstick one, but some cool tool you can use as well, which is quite cheap, is this simple SDR or digital TV receiver. You can find them from 10 to 20 euros online, and they can only receive in this case, but you could just do the same thing as I'm doing in this case as well, and then use another Arduino-like or Great Fat device with an extra component to transmit the signal. The yardstick is about 100 euros. This thing is 10 euros if you look to some cheap advertisements. So if we back up the signal from the switch, we will see a radio signal. And you can, with your computer, you can just load it as if it's MP3 in your audio player. And if you look closely, you might see it repeating a specific signal. And if you zoom in closely, it's quite easy to see a high or low signal. And like I already told, if you do this enough times, you will see patterns starting to come by each time. So you might at first think that a low signal is a 0 and a high signal is a 1, but I immediately recognize this as a pulse width modulated signal. You will do this. You can do this as well. Just practice a lot. It doesn't matter in this case, but I want to show you that you need to practice a lot in order to see these kinds of things. In the beginning, it's just high and lows. For now, for today, that's enough. So using the information we discovered, we can set the correct frequency. So on the packaging, we found it to be on the 433 megahertz range. In this case, I choose a specific type of modulation. It's not the same the device is using, but because I know it will be working, I just chose this one. So let's keep it there for today. And I set the baud rate, so the bits per second. And to give a bit more background on that, if you look in your MP3 player or your audio players, you can just see the timing or the high and the lows. So you can choose a baud rate that's able to capture all of those highs and low signals. And that what we do is we start recording the signal of the controller. And that's just a couple lines of code. In this case, we don't want to record all things, so we are looking for a specific signal strength. So the moment we see a radio message appear that's quite high in strength, then we know we have to start recording. So we don't fill up our whole hard disk with just data. But the moment we see the signal is of high enough strength, we start recording, and we can write each bit to a save file. And just a short signal. What you can do then is, instead of placing the yardstick in receive mode, you can set it in transmit mode and just replay the signal. In this case, the setup is quite the same. We will use the same frequency, we will use the same modulation, the same baud rate. We just replay the same bits we already received using the same hardware, using the same device. So to do the replay itself, it's actually quite a lot easier than receiving the signal. But in this case, I'm now able to switch on and off the light using my computer plus yardstick. The switch controller is a lot cheaper than the combination of those both, but I prefer it this way. And to give you an example of what you could do using the same hardware, I will show you my first car, my Mazda 6. And the reason I have two of them is because I wanted to hack or get in this thing. Nowadays we have the Flipper Zero, which is advertised to be able to do this as well. I don't think so, not without any extra components. But using two yardsticks, you are able to get in these types of cars. Because they use the same frequency as we saw early on for the switch controller. And it's quite easy. You need a bit of Python, a bit hardware, and just tinker around. I've been doing this in my weekends, so I think you can do this as well. Are there any questions?